We can do comparative study. We can do some standard samples.
रिकॉर्डिंग भी हो रहा है ना?
So Andrew is the person who revolutionized the NMR in the solid state, NMR spectroscopy in the solid state, because earlier people were not that much interested in recording the solid state NMR. Of course, physicists were interested because they wanted to study the magnetic properties, magnetic moment of the nucleus, different types of nucleus, etc. But chemists got interest, or chemists developed interest in doing the solid state NMR mainly because of the works of Andrew and his colleagues. Lowe, there is another person is also there called Lowe. So he revolutionized the NMR, in which they used a technique called magic angle spinning NMR, that's called mass NMR. Using that technique, you can generate high resolution NMR from solids. You can generate very sharp lines from solids. So once you get sharp lines, based on the literature survey and based on comparison with a variety of systems or similar systems, or based on experiments on known systems, people started correlating the NMR results. So this is one major milestone or major achievement in the history of solid state NMR, that the development of mass NMR, which is called the magic angle spinning NMR. Probably I will discuss in detail regarding the principle of magic angle spinning NMR, maybe after 1 or 2 lectures. So, but before this magic angle NMR was discovered sometime in the year 1980 and after that, because even though it was discovered around 1980 or 82, the technique came to existence in 1985 and 86. So then onwards only commercial solid state NMR spectrometer were developed, which can record this mass NMR, because there is some instrumental parties also there which need to take care for doing this mass NMR. So before that, the physicists were very much interested in recording the solid state NMR. I just thought I will show the photograph of this Andrew, who developed this magic angle spinning NMR and which revolutionized the solid state NMR pattern. In fact, you can get solution-like spectra from solids with line widths as low as that of solution. We can get from the solid state NMR, solid samples, using this magic angle spinning technique. So maybe you may also refer to 1 or 2 books if you are interested. These books are there in our library. One on solid state NMR in material science by a Russian author, Vladimir, and another one is by McKenzie. These are the 2 basic books which are available in our library. One more book is there which is with me, but these 2 are somewhat more basic than compared to the book with me. So why people are not interested in NMR and condensed matter? Because in 1936, there's a person called Cornelius J. Gorter. This is C.J. Gorter. He's a Dutch physicist. He spent a lot of time or spent a lot of years on lithium resonance from lithium fluoride and potassium resonance in potassium atom. He was interested in finding the magnetic moment of this lithium and as well as protons. But unfortunately, he could not get any signal. It was unsuccessful. All his experiments were unsuccessful. The reason, because he was not aware of that, the reason being that there was no relaxation, the nuclei like lithium and protons were not relaxing. If it is not relaxing, the signal gets saturated and you cannot detect the change in magnetization, because in NMR, what we use is a coil. Coil is only the detector. If you take a solid state NMR probe and see, you will see only one coil. This coil is used to see the change in magnetization by applying a pulse or whatever carrier wave or applying a pulse. So if there is no change in magnetization, you will not see a change in current. A coil will not detect a change in current and you will not get any signals. So that is why all his experiments failed, because there is no paramagnetic center or there is no paramagnetic impurities. These are highly purified crystals. He was keep on purifying the crystals. Lithium fluoride crystal, he made high purity lithium fluoride crystals to get the resonance. But all those experiments were unsuccessful. And in 1937, there was first gas phase. Some people have tried. There also people could not get NMR signal. The reason being that the now relaxation time, lack of paramagnetic resonance, etc. So in 1942, he kept on trying many years. I think 10, 12 years he tried and he was quite unsuccessful. But first successful NMR experiments in the condensed matter was did by Purcell and Bloch in 1945. I think in MIT laboratories they were trying. These are two independent physicists. They were trying and they were trying to evaluate or determine the magnetic moments of proton and proton. They successfully get proton signal from paraffin bags as well as from ice as well as from water. So at low temperatures actually. So later it is observed that the paramagnetic impurities present in these samples helped relaxation, and this relaxation helped to measure the signal from the sample. That is why they could get the signal. So then they, rather than detecting the magnetic, measuring the magnetic moment, they carried out detailed studies on the relaxation phenomena. And based on this relaxation phenomena, they made a theory called the BPP theory, which is valid for all solid state materials, or which is quite valid for condensed matter and in the condensed matter area. So this helped the understanding of relaxation from an active nuclei. Similarly, I think these people were awarded Nobel Prize in the year 1952 for getting signal, NMR signal from the condensed matter. So in that theory, only later Rowlin and Hatton modified the theory by introducing the correlation time TC. So later, probably after a few classes, maybe after 5 or 6 classes, I may explain how the correlation time determine the line width of this one, line width of the NMR in solid state. Correlation time and this temperature, how it depends, how it affects the line shape of the NMR signal. So then later various theories were produced like energy, there are some defects are present in the lattice, and this defects in the lattice helps for the energy migration from due to dipole-dipole interactions, and all those theories were performed. And this only eventually led this Purcell to get the Bloch and Purcell to get the Nobel Prize. So again, further Japanese scientists again modified that equation. So in the equation and all, we will not be going into details. But these explain qualitatively why the line width of solution NMR is much smaller than that of the solid. They demonstrated with the help of H1 NMR of water as well as ice. So you see a difference around 30 megahertz NMR they were doing, and they see almost a 10 raised to 5 times more line width when it becomes ice. So this has been beautifully explained in the case of the correlation time. Correlation time I will discuss. It is nothing but the time between the magnetic field fluctuations. So coordination time, if you multiply with the omega 0, which is the operating frequency, you will get a number. If it is very, very less than 1, you will get a very narrow line shape. And if it is very, very greater than 1, you will get a broad line shape. Probably I will discuss this aspect when I discuss the relaxation time. So as I mentioned in the earlier, the advent of magic angle spinning NMR in the year 1980 by Andrew revolutionized the solid state NMR, and the chemists started working on solid state NMR, and a lot of interest, and people started devoting a lot of interest on solid state NMR to get information. As I mentioned, why there is a difference in solution state and solid state NMR. In solution state, what happens? We have a random Brownian motion is there. So the interactions get averaged out. Suppose you take anyway, if you take sodium chloride solution, if you put sodium chloride in water, it dissolves into sodium ions and chloride ions. So these sodium ions will have water molecules, will have chloride molecules, and also will have sodium ions in solution. So we do not know how many sodium ions at a particular point in solution will have near neighbor of sodium, chlorine, and water, because they are randomly moving. It is very difficult to say how many number of sodiums are there, how many number of chloride ions are there, because they are randomly moving. Once anything randomly moving, the interactions gets averaged out. Sodium 23 is an NMR active nuclei. So as the number of near neighbors or the number of near neighbors changes so rapidly, then the interaction between the ions gets averaged out, and there will be negligible interaction. So due to this negligible interaction, what we get is a very sharp line, narrow line width. So you can get information what is the environment around sodium. We can normally, if you put sodium chloride, sodium ion will be hydrated. So the hydrated sodium ion will be characterized by a very sharp line. But instead of that, rather than putting in water, take sodium chloride and grind it very well. And if you take an NMR spectrum of sodium, you will get a spectrum, whatever I have shown in the above, something similar to that. It is not exactly a typical case I have written. So anyway, so sodium is a 3/2 nucleus, half integer, not half integer nucleus, plus half nucleus. So it will be, spectrum will be somewhat similar to that. You can see how much line width you see, large line width you see, more than, I have not mentioned the axis points, but it is more than 100 kilohertz. So you may, first look, you may see what information I can get. This line shape is giving such a broad pattern. What information we can get, we will be confused first. But if you analyze this properly, what you can get is the interaction between the sodium ions. Initially, people thought this is not good. Whatever we are getting is a broad line shape is not good. It is not possible to get the interpretation. It is not possible to do interpretation, and it is not possible to get any meaningful information from such line shape. But later, with the development of the relaxation theories, as well as the modeling of the dipole-dipole interaction between the sodium ions as well as the proton, people were able to get information. People were able to predict the line width as well as the line shape. And once they understood the line shape and how it will be the line width, then they were able to get information regarding the internuclear distance between sodium ions and chloride ion, etc. In fact, there are papers in which by using sodium chloride as a sample and by recording 23 Na mass NMR, they are able to get a reasonably good information on the distance between the sodium and chloride ion as well as the distance between the two sodium ions. And this they could match very well with the information obtained from the X-ray diffraction patterns. So I just gave an example of sodium chloride. If you take sodium chloride, now this is anybody must be knowing, all people must be knowing what is sodium chloride. It is an FCC structure, and each sodium is octahedrally coordinated with the chloride ion. In the case of solid, in solution we cannot say. Solutions and ions are randomly moving. For a given sodium, there are 6 chloride ions as next near neighbor at a distance of d. D is nothing but half of the lattice parameter, which is nothing but a/2, and another 12 sodium ions at a distance of root 2d. Root 2d is nothing but a/2, it will become a/√2. At a 12 sodium ions at a distance of root 2d from a particular sodium ion, that is called a next near neighbor. First is near neighbor, and then another is called the next near neighbor, and then next to next near neighbor. That is the third one. So like that we have at a distance of root 3d, we have 6 sodium ions, our third neighbor. And then we have, sorry, I have written Cl2 minus, sorry for that. There are 24 chloride ions at a distance of root 25 times d. And there are 24 Na ions. So you can see the number of, if you take a particular sodium ion, you have different number of sodium ions as well as chloride ions as near neighbors. First near neighbor, second near neighbor, third near neighbor, etc. So if you understand this structure, you may be able to model what type of interactions are possible with the first near neighbor, second near neighbor, third near neighbor, etc. So they will give some terms, and these terms can be introduced to get the line shape. So that way you can simulate the line shape, and from the simulated line shape, you will be able to calculate what will be the distance of first near neighbor sodium ions, which are at a distance of first near neighbor is anyway chloride ion, because sodium chloride is an ionic lattice. Near neighbor, first near neighbor around sodium should be negative charge species, so chloride ion should be first near neighbor. Second near neighbor should be sodium. So by doing that, we will be able to find out how many sodium ions are there around a particular chloride ion, and how many chloride ions are there around a particular sodium. So this information is similar to what you get from XRD. In XRD also what we will get, XRD also we get bond length. Once you know the bond length and once you know the geometry, we will be able to calculate the ionic radii, and from the data table we know the ionic radii, and you will be able to calculate the bond distance. Once we know the bond distance, we can say what will be the distance, what is the neighbor distance, near neighbor distance and next near neighbor distance. So NMR and XRD, X-ray diffraction, go hand in hand to predict the crystal structure of this material, okay, any material. So this I have got a simple example. Like that you can do for a variety of material like alumina, silica, silicate, etc. I may be giving some example maybe after 3-4 classes. So in solution, I told solution because of the random Brownian motion, all the interactions must be getting averaged out. So which I have explained clearly. But in solids, there is interaction. These interactions will never get averaged out. Of course, there are ways to average out, but one cannot completely get averaged out. Average out these interactions. So this scheme, this slide, if you see, I am just trying to explain what are the interactions which are existing in the solid state. The typical example of interactions existing in the solid state. We have a nuclear spin I and we have a nuclear spin S. Typical case, for example, if you take any organic molecules, we can say proton can be considered as spin I and carbon-13 considered as spin S. So if you see, for example, in an aluminum silicate, if you take, and sodium, silicon can be considered as spin I, and aluminum can be considered as spin S. So if you consider this case, the spin I, let us concentrate on spin I, nuclear spin I. See, this nuclear spin I have an interaction called 1. This 1 number corresponds to Zeeman interaction, which is nothing but the surrounding magnetic field. So Zeeman splitting already in the previous classes, you might be aware from the previous lectures, you might be aware the Zeeman interaction is nothing but the interaction of the magnetic field, the nuclear energy levels, nuclear spin energy levels. So this number one interaction is nothing but the interaction of nuclear spin with the magnetic field known as nuclear Zeeman or Zeeman effect. What is the interaction 2? The interaction 2 is nothing but the interaction between spin I and the interaction between spin S through space. Through space. And this through space interaction is called a dipole-dipole interaction. This dipole-dipole interaction is the major thing which governs all solid state NMR line shapes. So this dipole interaction is very strong between the type of few kilohertz to megahertz. So that can be averaged out by some experimental technique, but that we will discuss it later. But this interaction exists in the case of solids, and that interaction is not there in the case of solution because of the random Brownian motion. So the interaction number 2, which I have shown with a double-headed arrow, is nothing but the dipole-dipole interaction. Then what is the interaction 3? The interaction 3 is nothing but the interaction of the nuclear spin I or nuclear spin S with the electron spins. Electron magnetic moments are much larger, almost 2000 times larger compared to nuclear spins in general. So the interactions are very high. The extent of interaction is very high. So the nuclear spin can interact with electrons. So this happens because of the paramagnetic centers present, or in the case of quadrupolar nucleus, which I will explain later. A quadrupolar nucleus is nothing but a nucleus which is non-spherical in nature. So such nucleus, there is an electric field gradient. So this aspect I will discuss it later. So this you can say the electrons are nothing but the paramagnetic center present in the system, or it can be because of the quadrupole effects. And what is 4? 4 is nothing but simple thing. 4 is nothing but a nuclear spin interacting with the lattice. It can interact with the lattice, can have a nuclear spin lattice interaction, spin lattice relaxation, etc. Probably you might have learned. So the interaction number 4 is nothing but the spin lattice interaction. Because in the case of a solution, there is no lattice possible. If there is no lattice, there is no concept of phonons. Phonons, everybody must be knowing by this time, phonon is the basic unit of lattice vibrations. Like photon is nothing but light quanta. So phonon is nothing but the quanta of lattice vibrations. So lattice vibrations have an effect on the nuclear spin, either I or S. So that interaction is called a spin lattice interaction. That is denoted by the number 4. So interaction number 5, anyway, we will not discuss because nothing but the electron phonon interaction, which we will not come to know. But if you see the interaction 3 to 6, if you see a nuclear spin is interacting through electron to the magnetic field. You can see here, nuclear spin is interacting through electrons to the magnetic field. This gives nothing but the chemical shift environment. The interaction 3-6 is nothing but the chemical shift interaction. So these are the main interactions in the case of solids actually. These are also explained here. The first one I told is even interactions of nuclear spin. So the second one is nothing but the second is nothing but the dipole-dipole interaction, which I have told. It is not there in solution, only there in solids. So which we need to average it out to get a good signal or a sharp signal, meaningful information. And the third one is nothing but the nuclear electron interaction. The third one which I have written, nuclear and the electron interaction. It can be the J coupling, because it can be through bond also it can couple. So it can be a J coupling, or it can be nuclear electron coupling, or coupling of nuclear field with the molecular electric field gradients, particularly with the quadrupole nucleus. Sometimes there's a fluctuating molecular electric field gradients. All those is denoted by the interaction term 3. 4 is nothing but, as I mentioned, it is a direct spin lattice interaction, because phonons are there only in solids. So there is a spin, nuclear spin and phonon interaction. So that is nothing but the spin lattice interaction. Spin lattice relaxation come from that. And 3 to 5 is what? Indirect spin lattice interaction. Okay, indirect spin lattice interaction means 3 is nothing but nuclear spin is interacting with the electron, and the electron is interacting with this phonon. Phonon is nothing but the lattice. So 3 to 5 is nothing but not a direct spin lattice interaction, but an indirect spin lattice interaction through electron. So that is called, it is 3 to 5 is nothing but an indirect spin lattice relaxation. Whereas 3 to 6 is nothing but the chemical shift or chemical shielding interaction, because you can see the 3 is nothing but the interaction of nuclear spin with electron, and this electron interact with the surrounding nuclear magnetic field. So that is nothing but the chemical shift or chemical shielding or polarization, etc. So 4 to 7 normally we don't encounter a coupling of nuclear spins to sound field. That we will encounter. We are not discussing in this lecture. Probably we will discuss it later. Although these are the interactions, mainly the major interactions, of course there are some, I think with the software, I think I could not give this. Proportionality signature is appearing as a proportionality symbol is appearing as a question mark. Sorry for that. The main interactions which we study, these are all the interactions which are present in solid, but the main interaction we will be focusing is nothing but the dipole-dipole interaction.
पेन से कर दो ना, वो तुम्हारा ओरिजिनल में नहीं होगा।
ओरिजिनल में नहीं है।
देखो पेन में ना एक पेन, वो उसको नहीं जाएगा। आप पहले इधर लेके आओगे ना, तो ये पेन आया, इसको सिलेक्ट करो। सिलेक्ट करने के बाद ना आप इधर प्रोपोर्शनलिटी कर दो, वो आप इरेज नहीं कर सकते।
ये डाटा इसे
नहीं, आप कैसे ऐसा कर दो?
It should not touch it, ना?
नहीं, ऐसे you can do it this way ना। Proportionality you can draw this way ना।
हाँ, yes, yes.
इसका जस्ट वही कर दो, ओरिजिनल में चेंज नहीं है।
चेंज, okay. I think next time I will change the.
शॉक कर दो, right, right, right. जिधर भी है ना,
Okay.
ठीक है।
ठीक।
हम इसको अगर इरेज करना है ना, आप देखो इरेजर है।
Okay, okay.
इरेजर,
Okay.
इधर आएगा, इरेजर आता है।
Okay, इधर है।
हाँ, इरेज करने के लिए मैं यूज करता था इरेजर, ऐसा है, जो भी है। हाँ, अभी इरेजर आया, ठीक है। अभी आप लिख सकते नहीं, आपको
टच नहीं,
हाँ, स्क्रीन टच नहीं करना पड़ेगा, राइट। हाँ, एक दो दिन प्रैक्टिस करो तो हो जाएगा।
So main interaction, although I told around 6 to 7 interactions, lattice interactions, spin lattice, electron nuclear coupling, quadrupole and all those things.
तो थीटा भी नहीं है, cos square थीटा भी नहीं है। Cos square थीटा ना?
हाँ, cos square theta is not coming.
Theta.
Here also theta should be there.
Right.
I think version to version it changes, I think.
Actually आपने वो insert symbol करोगे तो नहीं होगा।
हाँ, I think tomorrow I will do that. Next class I will do.
Insert symbol करोगे तो problem है।
3 cos square theta. See, dipole-dipole interaction we will discuss in detail, but if you see the dipole-dipole interaction expression, there are radial part and there is an angular part. This angular part is having a dependence of 3 cos square theta minus 1. What is theta? Theta is the angle which the bond vector between the two spins make with the magnetic field. See, in the figure you can see I have drawn a vector, bond vector between I1 and I2. It can be I can be proton and carbon, I2 can be C13, or it can be silicon and aluminum or any nucleus. sodium and aluminium or sodium and silicon. So I1 and I2 is separated by a distance called bond vector. And this bond vector makes an angle theta with the applied magnetic field. B is nothing but the applied magnetic field. Somehow, if you can make all the bond vector at an angle theta with respect to the applied field, and then if you can manipulate theta in such a way that if cos squared theta become 1 by 3, then the dipole interaction can be averaged out. How we will do this averaging out, we will discuss it. So that is why we are telling this dipole-dipole interaction is having an angular term of 3 cos squared theta minus 1. Similarly, we have also a quadrupolar interaction. What is this quadrupole? Many of the nucleus are quadrupolar in nature. If you see the periodic table, many of the nucleus are quadrupolar in nature. Typical examples are sodium, nitrogen. Nitrogen 14 is quadrupolar in nature, like deuteron. Then aluminium is a very popular nuclei in the case of solid state. Then many of the nucleus are quadrupolar in nature. What do you mean by quadrupole nature? Quadrupole nucleus is nothing but a nuclear which is non-spherical in shape. If it is spherical in shape, charge distribution within the nucleus is symmetrical. If there is non-symmetrical charge distribution, then dipole moments. Whenever there is an asymmetry in charge distribution, what do we know? There is a dipole moment created. Similarly, there is an asymmetry in the charge distribution of the nucleus, and this leads to the quadrupole moment or the dipole moment, you can say. But since this is a quadrupole nucleus, the terminology is given as quadrupole nucleus, we call it as a quadrupole nucleus, and this is called a quadrupole moment. So this quadrupole interaction is having multiple terms, and multiple terms have multiple radial terms and multiple angular terms. But so at least 3 terms, first order, second order, third order terms are there in the case of quadrupole interaction. At least first 2 terms have an angular dependence of 3 cos squared theta minus 1, where theta is nothing but the angle the bond vector makes with respect to the applied magnetic field. Then we have chemical shift anisotropy. Why this chemical shift anisotropy is coming? Because as I mentioned, in the case of sodium chloride or any solid state material, atoms are fixed. So the electron cloud is not symmetrical. In the case of a solution, electron clouds are symmetrical. In the case of solid, we don't have a symmetrical electron cloud. You see the electron cloud is looking like a coconut. If you see vertically, it looks like a coconut. Actually, it is not a symmetrical electric field gradient or electric field distribution. So whenever there is a asymmetry, we have components. If there is no asymmetry, components will be same in all the direction. But whenever there is an asymmetry, there is a component in the x-axis, there is a component in the y-axis, there is a component in the z-axis comes into picture. So this will not get averaged. This will get averaged out to a certain extent, but it is very difficult to get completely averaged out. This will remain with the NMR, and this people have made it as an advantage for getting information regarding the environment around x, y, and z directions around a particular nucleus. So I have given also typical values of this coupling constant, like 10 raised to 2 to 10 raised to 5 hertz for dipole-dipole coupling. And quadrupole interaction, normally there's a very broad range depending upon the environment it changes. For example, if you have a cubic symmetry, if you have an octahedral symmetry, or if you have a cubic 8 coordination symmetry, then it is more or electron cloud distribution is more or less symmetry. So you will have a very low value of quadrupole coupling constant. So that is why I have written 10 raised to 0 also. But if you have a completely asymmetric structure, like a very poor symmetry, like 3 coordinated or 4 coordinated, and it is deviating from tetrahedral geometry, then all those cases, the coupling constant will increase. Let me go further. So as I mentioned, I thought I will just give you an indication what is a quadrupole nucleus and what is a spherical nucleus. This slide very clearly shows spin half nucleus. You see, the spherical in shape. It's like a ball, football. You can see charge distribution is spherical. Whereas in the case of a quadrupole nucleus, you can see charge distribution itself is asymmetric. In addition to that, we have an environmental problem. Environment also will not be symmetrical. Only in very, very typical and specific cases, we get a very spherical environment. So in most of the solids, the environment will be highly asymmetric. So we will have coupling coming from the environment also, and also the coupling coming from the nucleus also. So whatever is written in red or whatever shaded with brown color, brown or orange color is nothing but they are all quadrupolar nucleus. whereas the spin-half nucleus are white in color. It is having a blue black background. So you can see the spin-half nucleus are much smaller compared to that of the quadrupolar nucleus. Quadrupolar nucleus is large in number. So it is necessary to understand the quadrupolar interaction, how the quadrupole line shapes gets affected by change in the environment, etc. Because that will help you to get a lot of information from solids by using NMR technique. So these are some of the expressions from the spin-half nucleus. So spin-half nucleus, what happened, as I mentioned, in the case of a solid, we do not have in the case of a spin-half nucleus, we have a sphere. So we have, but even though it is a sphere, the electronic environment can be asymmetric. So we have components, sigma, components of the shielding. Shielding is called, they call it as not a vector, it is a tensor. I will discuss it later. But the shielding has also components. It is having different components. It is having components in the X, Y, and Z directions. So that is why I think I will discuss it later, because just I thought I will introduce this concept. So shielding also having a components like sigma 11, sigma 22, sigma 33, etc. These are the components of the shielding tensor. How this shielding tensor comes, probably in the subsequent slide today or tomorrow, I will discuss that aspect. These are nothing but the normally vector, vector is nothing but a magnitude and direction. So vector of a vector people call as tensor. So tensor is normally represented by a matrix. So you will have sigma 11, sigma 12, sigma 13, then sigma 21, sigma 22, sigma 33, like 9 components will be there. So once you have a 9 component, we can diagonalize that matrix. And once you diagonalize that matrix, we get only diagonal components. So diagonal components are nothing but sigma 11, sigma 22, sigma 33. So these are done by a phenomenon called axis transformation. So by doing this, you can get the isotropic chemical shift. So that is the main thing which I want to convey through this. Probably this when I discuss examples, this aspect we will discuss further. So similarly, quadrupole moment also, there are expressions to calculate the quadrupole moment, and using this expression, one can get the quadrupole moment and compare with the literature. What is the environment? If you have a very high quadrupole value, we can say it is either very low coordinated or whether very low symmetry, or if you get a very small value of quadrupole coupling constant, we can say, of course, it's a tetrahedral symmetry or a cubic symmetry or a octahedral symmetry. That type of judgment you can make by measuring the CQ values. CQ values can be easily calculated. Nowadays, programs are there, but earlier people used to fit the NMR solid state NMR line shape to get the value of CQ. CQ is nothing but the quadrupole coupling constant. And E is nothing but the charge of the electron, and Q is nothing but the charge of the surrounding electric field gradient. So Q is nothing but the charge distribution. Q is nothing but the charge of the nucleus, capital Q. So maybe one example towards the end, I think maybe in the 8th or 9th lecture, I may give one example how to calculate the quadrupole moment or quadrupole coupling constant CQ. CQ is nothing but the quadrupole coupling constant from quadrupole NMR of the quadrupole nuclei, like boron, typical NMR of boron. Boron is a very, very important nuclei for us because borosilicate glasses contains a lot of boron. So we need to understand what is the environment around boron. So quadrupole coupling constant can be very well used to find out whether it's a tetrahedral or whether it's a trigonal or whether it's a pentacoordinate boron, etc. So before going to the actual chemical information obtained from NMR, just one more terminology I will explain. That is nothing but the night shift. There is something called a night shift. Night shift is applicable for metals. Because in the case of a metal like sodium, potassium, and also like noble metals like gold, platinum, silver, palladium, etc., their electron clouds are there. They are called free electron clouds. They are quite delocalized. Sometimes people call it as a Fermi gas. In solid state science, they call it as Fermi gas, where the electron interaction, unlike transition metals, are not that strong. They are completely correlated actually. The electron interactions are very, very less. So in such cases, if you keep that metal in a magnetic field, this conduction electron get polarized. And this polarized conduction electron can create a magnetic field at the nucleus. So if you take a sodium metal, we will get a particular frequency of resonance. But if you do a sodium chloride, which is nothing but sodium ion, you will get a different frequency. So this difference in frequency, we call it as the night shift. The night shift refers to the relative shift K in NMR frequency for atoms in a metal compared with the same atom in a non-metallic environment like sodium chloride or sodium bromide or sodium iodide. So previously, people were measuring this mostly physicists, chemists were not doing such type of work. Previously, physicists were working on evaluating the magnetic moment of atoms, particularly in the vapor phase they were interested. So they would want to compare how the magnetic moment of atoms changes in different solids, particularly of sodium in sodium chloride, or in gas phase, or in sodium metal. So they were studying this type of interactions and measuring the night shift. And also, many people were studying also hydrogen storing many metals, people use store hydrogen. So when hydrogen interacts with the metal, what happened to this night shift? There are a lot of people, including people from ERC, were studying what happened, the night shift, when hydrogen absorbs in a metal, because like platinum, palladium, etc., they have a tendency to absorb hydrogen. So with hydrogen incorporation, the free electron gas or the delocalized electrons, nature changes. And this nature change is resultant in the shift in the night shift values or the shift in the K values. So this is a very good parameter used to characterize the change in the electronic cloud or the free electron cloud in a metal. So various theories have been explained, which we will not go into details. Various theories like polyparamagnetic susceptibility, Fermi contact interaction. These are some of the explanations given. The polyparamagnetic spin susceptibility comes from the free electron theory itself, and S wave function, that is nothing but the Fermi contact interaction also is the same terminology is there also in ESR and also in NMR. So these are the two parameters which the people say because of this there is a effect of conduction electron on the nucleus, and this effect of the influence of conduction electron magnetic field on the nucleus occurs, and this results in the change in the chemical shift values, and which is denoted by the night shift. So let us go further. So I have tried to give an explanation because I am not going to discuss much in next classes all those things. So night shift people were very solid state physics, and including some material scientists were very with a lot of interest. They were working on night shift and got a lot of information which can be correlated with respect to the relaxation time in metals, etc. So another very interesting thing called Corringer relation. Corringer relation is nothing but this relation between spin lattice relaxation rate and the night shift. So people have observed, people who work on metal and magnetic moment of metals and alloys and hydrogen storage material, people have observed that in the case of metals and alloys, if you measure the relaxation rate as a function of temperature, you get a linear relationship. And this linear relationship can be expressed by this type of relation. R1 by K square is nothing but a constant into temperature. What is R1? R1 is nothing but the spin lattice relaxation rate, which is nothing but the inverse of T1. T1 you might have studied. T1 is used for measuring the lot of time people might have studied the T1, the spin lattice relaxation. In solution NMR also people many times measure this T1. T1 is an important parameter also because it decides the pulse width and delay time, etc. So if you know the T1, you can calculate 1 by T1 is nothing but the R1. So once we know the R1 and if you know the night shift, and you can plot this as a function of temperature, and you get a parameter called a Curie, this constant called the Corringer constant. The Corringer constant is a parameter which depends on the electronic density of a changes in the free electron distribution or the interaction within the free electrons, etc. So this electron is, in other words, the Corringer constant is C is nothing but which parameter which determines the electron distribution in the solid. So a lot of correlation has been made with the material properties like thermal expansion, dielectric properties, etc. with this Corringer constant. So there is also a pseudo-fluid NMR in the case of solids in ferromagnetic systems. Probably we will give one example towards the end of this course, maybe 10th or 12th lecture, we will give one examples of a Fe3O4, which is nothing but an inverse spinel in which you can detect signals from iron nucleus without applying any field. So now let us see what is the chemist point of view. So far I have been discussing many times about what physics people do, what physicists do, what are their interests, and what information, what way NMR helps, solid state NMR helps the physicist. Of course, it will be help the material scientist also. Nowadays there is no boundary between the fields, physics and chemistry all are now overlapping. So what information a chemist can get from solid state NMR? The first and foremost information that we get is the number of nuclei in structurally different environments and their orientation and their mutual disposition. For example, if you take nuclei like silicon, aluminium, boron, sodium, etc., they have a variety of coordination environment. In many inorganic solids, if you see boron exists in BO3 configuration, they have trigonal geometry. But in many compounds of boron, many of the inorganic borates, boron exists in tetrahedral coordination, BO4. BO4 minus I should put because there's a negative charges there. So BO4 minus, I forgot to put minus. Similarly, ALO6, ALO5, ALO4, SiO, Si, variety of linkages are there in the case of inorganic materials like boron, containing boron, aluminium, etc. So similarly, what happened in the case of silicates also, we have silicon, oxygen, silicon. Then again oxygen comes and then again silicon comes. So if you take first silicon, then near neighbor is oxygen. Second neighbor is silicon. Third neighbor is again oxygen. And fourth neighbor can be again an aluminium or boron or sodium or potassium or any other ion. But the NMR, solid state NMR, is sensitive to changes even at the second and third near neighbors also. So this makes the solid state NMR a versatile technique for understanding the structure of borosilicate, boroaluminate, aluminosilicates, etc. Why I explain why this borosilicate and aluminosilicate I explain because this boron, aluminium, etc. their atomic number is quite low. Once their atomic number is quite low, it is difficult to get good quality diffraction patterns. You may be all knowing because diffraction pattern depends upon the number of electrons present in the atom, or Z is nothing but the atomic number of the element. If the atomic number is low, like boron, carbon, nitrogen, etc., it is very difficult to get, particularly with the nitrates, etc., it is very difficult to get good diffraction information because they are in low Z values. In such cases, if you see, NMR leads. So NMR wins in such cases because NMR is highly sensitive for such nucleus like boron, aluminium, etc. Then this is one type of structural information. So once you get structural information, you will be able to correlate the physical properties because in many of the material, the geometry decides the thermal expansion of the material. Thermal expansion coefficient is structural property. Any structure, if you want to make, you need to know the thermal expansion coefficient. People say dialectometry. Dialectometry experiments you have to do to evaluate the structure, to understand the strength of the material, bond energy of the material. Similarly, this also can give information regarding the thermal conductivity, bond vibration energy, and also the band gap. If you have a very strong covalent bond, what happens? Normally the band gaps are higher, but as this bond strength decreases, the band gap also decreases. Not true in all cases, but by and large. So this information also we can get bond order, also you can get from NMR studies. Maybe I will give one or two examples after 3-4 classes. Another example is the dynamic behavior of groups. So many times what happens, the groups start moving. Like in the case of organic molecules, it is frequent, like trimethyl ammonium bromide, if you see the ammonium groups undergo motion. Similarly, many of the groups like PF5, many of the phosphorus fluorides, many of the antimony fluorides, etc. If you increase the temperature, they start moving. The groups moves. So groups moves means what happens? The relaxation time gets affected, and also as I mentioned earlier, the dipole-dipole interactions gets affected. Once the dipole-dipole interaction gets affected, then we see the modulation of the dipole-dipole interaction, and this modulation leads to changes in the line shape as well as the chemical shift values. And the third and most important is nothing but it helps to understand the phase transitions. For example, if you take a typical alumina exists in mainly two forms, alpha form and the gamma form. Beta form is quite different. It is nothing but it contains some sodium ions also. The alpha to gamma transition leads to change in the aluminium environment. Alpha to gamma transition leads to change in the aluminium environment. So whenever there is a change, because there is a coordination, in fact, even though it is a tetrahedral and a octahedral coordination changes, this can be easily monitored with the help of aluminium NMR. For example, in alpha aluminum, aluminum exists in both tetrahedral and octahedral coordination. But if you heat it, what happens? The tetrahedral gets converted to octahedral aluminum. That is in gamma aluminum. Alpha alumina is called corundum. The gamma aluminum exists only in octahedral configuration. So this phase transition can be modeled or can be monitored with the help of this aluminum-27 and solid-state nuclear magnetic element. Then another important aspect is the cation mixing in glasses. You may be knowing many people glasses, borosilicate glasses have a lot of importance in atomic energy, in Department of Atomic Energy. And borophosphate glasses in Russia and all people are telling that they are using mostly phosphate glasses, whereas in India, mostly we are well experienced with borosilicate glasses. In borosilicate glasses, how boron and silicon mixes, this is an important aspect. This information we cannot get by XRD, X-ray diffraction. NMR is the only technique we can give information regarding the mixing of cations in glasses. Because first of all, it's a low Z element. And second, even you cannot use XPS, X-ray photoelectron spectroscopy, because the Z number is, atomic number is low, so you may not be able to get good quality X-ray photoelectrons from this. So with the help of a boron NMR, we can get beautiful information regarding the cation mixing, particularly the boron structural unit present and how the boron structural units are mixed with the silicon structural units in glasses. Similarly for polymers and blend carbon-13 NMR. Carbon-13 NMR people do extensively to understand how different structural unit or different backbones are linked, different units are linked, chain linkages in polymers. So, and also in the case of polymers, as a function of temperature, the polymer, the groups present, they undergo softening, the groups or the polymer gets softened, and accordingly the movements happens with these polymer molecules present in the system, and this also can be monitored with the help of carbon-13 NMR. Another very important aspect is the phase homogeneity. Phase homogeneity, this I will give you typical examples in the next class, because I thought I will just cover these basic aspects of NMR in the first lecture, and then next lecture onward we will go for magic angle spinning NMR, how you reduce the line shape, and give some typical examples, and we will discuss that type of examples. So phase homogeneity to the length scale of few angstroms you can get. That is the most important aspect, because the NMR gives the environment around a few angstrom, whereas X-ray and other neutron diffraction, X-ray diffraction or electron diffraction, etc., you require long-range ordering to the length scale of few nanometers or at least up to 100 angstroms. More than that, only you can get meaningful information. But NMR probes within angstrom, less than 10 angstrom you can get information, or less than 5 angstrom also you can get meaningful information from NMR. That way, one can get information regarding the short range order in variety of materials. Another thing, also, there is, in particular in glasses, there is called a medium range order. Medium range order is also difficult to get by other techniques like XRD or diffraction techniques, XRD and neutron diffraction or other vibration technique. Whereas the NMR also gives, because of these near neighbor interactions and second near neighbor interactions, and by performing multi-nuclear or multi-dimensional NMR, you can get information even the third near neighbor as well as fourth near neighbor, and this can give the medium range order in different types of glasses. So these are a lot of information. This type of information you can get by using solid state NMR. So another important aspect is protein folding. Probably many of the people who are working in biology must be knowing protein folding is a physical process by which a protein chain is translated into native three-dimensional structure. So you see folded protein, you can see on the right-hand side, you see folded proteins. The other protein is not folded on the left-hand side. So what happens once protein gets folded? There's a significant changes in the dipole-dipole interaction. In solution, many times these interactions we will not see. Of course, there are methods to see that, but the interactions gets averaged out more or less. But if you go to solid, this interaction will not get averaged out, and you can get a lot of information of protein folding, etc., by performing this C13 NMR experiment. There's a slight modification C13 NMR we do in the case of solid called cross polarization. This aspect we will decide maybe after 2-3 classes. So this C13 NMR, modified C13 NMR, in solution state we use it somewhat different type. In the case of a solid, we use a C13 NMR called the cross polarization technique. So using that technique, using that you can, for the time being, you believe it as C13 only. Using that C13 NMR technique, we can get a lot of information regarding the dipole-dipole interaction in the folded protein, which is biochemically active, and this dipole-dipole interaction will give you the distance between the atoms, and this information will be quite useful, and one can compare also with the crystallographic studies available for the proteins. So these are two basic expressions probably you might have encountered in your previous classes. One is the magnetic moment, nuclear magnetic moment, because anything is always a nuclear you consider as a magnet. So magnet will have a magnetic moment mu(n). So mu(n) can be expressed this type of relation. So this I will not discuss much because this is, you must be already coming to, you must be already well aware of that. Then magnetic component of I we have Mi plus half and minus half, probably I will not discuss. Then some books, if you see, mu, as I mentioned, magnetic moment is nothing but H cross into gamma n into I. Gamma is nothing but the gyromagnetic ratio. Gn is nothing but the nuclear G factor. Gn and gamma n are related. So there is, and if you see some other books, you can see this type of expressions also. Mu is nothing but the gamma p. These are the classical expressions. So and p is nothing but the angular momentum, and mu is nothing but the magnetic moment. These are some of the expressions I am not going to discuss in further lectures, and this ends here. So these are the terminologies which I will not be discussing. This probably you might be aware also. In the previous classes, you might have already, this topics might have discussed on the previous lectures. So this also you must be knowing. This also I will not discuss. Gamma value, if you see, gamma is nothing but the gyromagnetic ratio. Gamma is the highest value for proton. So why I told this gamma value mentioning here is that once the gamma is higher, the dipole-dipole interaction is higher. So that is why protons have the most highest value of dipole-dipole interaction. So that is why in solids you don't see much proton NMR. In solid only people go for C13 NMR because the gyromagnetic ratio is very high, and the gyromagnetic ratio comes in the expression for dipole-dipole interaction, and this makes the dipole-dipole interaction very, very high, and it is very difficult to average out this proton dipole-dipole interaction. So that is why people, most of the time people do heteronucleus only rather than proton in the case of a solid. In the other cases like carbon-13, etc., this is relatively less. So you can see, so people extensively use neutron NMR, carbon, nitrogen, C13, N15, O17, etc., or as a solid state NMR. This also I will not discuss. So here onwards, I think I should explain to you, because the most important information which we get from NMR is nothing but the chemical shift interaction. So chemical shift interaction is the this information we get from solid state NMR. So shall I continue or should I? So you can, to this, I think probably this involved some of this tensor and I will explain. So next class, continuity will be there. That is why.
You can tell them that they should go through these basic things.
Yeah. Kindly go through this. I think slide is there. I think in the
slide is there, and also these the fundamentals of NMR.
Yes.
There were 10 classes taken by in the part 1.
Okay.
Which was taken by by one professor from Niger. They should see he is from physics actually.
Yes. Okay.
The physics of this NMR.
Okay.
It took 8 classes.
Okay.
So you should see the first 8 classes of NMR.
Yes. Kindly see the first 10 lectures on regarding the basic NMR, in which all these terminologies like energy level splitting for a, how it will be different for a spin half nucleus, how it will be different for a spin half nucleus, how it will be different for a quadrupole nucleus, what are the different gamma values, and what are the expressions available. All these things might have already taught to you or must be available in the previous first 10 lectures. So kindly go through that so that you will get a feel of that. So these things we will not be discussing in the next lectures. So I will be directly going to what information we will get by giving examples from solid state NMR. So this aspect will be discussed.
We just give them a chance if they have any doubt.
Yeah. Please feel free, and any clarification or any doubt or any question.
And also, also ask the participants to register their participation.
Okay.
Anurag ji,
all students or all participants must kindly register for this lecture, so that I can also see who are the participants which are there online.
Your attendance. Attendance,
Attendance.
attendance, they should write in the chat box their
Okay.
registration number.
Okay. So
That information was given at the beginning only. I think two were the Samim Molla and one more has joined. And Sivangi. I
Okay.
could see two only. This is from here and we have to see in YouTube also.
Okay. So all participants kindly this attendance. Your attendance in the chat box.
सबको कॉपी कर लो.
So all participant, any doubt or any clarification, I will be happy to interact with you. You can stop at any time. It is not that you should wait for me. You can stop at any time, then I can discuss.
कोई तो आज तो किसी ने क्वेश्चन नहीं पूछा.
हाँ, आज किसी
हमको बोलिए that next class is on Wednesday at 3:30.
Okay. So kindly note that next class is at 3:30. Please attend. So go through the slides.
On Wednesday.
Wednesday. Next class is at Wednesday, and we have 3 classes in a week: Monday, Wednesday, and Friday. All classes are at 3:30 to 4:30. Please be present for the lecture. So any clarification you can mail me also, or you can ask in the chat box also, or you can raise your hand. Hand raising possible, no? Yes. Okay.
Sudarshan, you also share your email ID with the participants. You can give it to Anurag.
Next lecture, na?
Okay, next lecture I will. Okay, I will write it on the.
First you give your email ID so that they can communicate you directly also.
Okay.
Or they can send to the time being. They can send the help करके जो इन्हें ना help NMR.
Yeah. That email ID is already there.
NMR email ID is there. They can send so that it will be available to us.
So my email ID is vsudar@barc.gov.in.
Dr. Anurag ji,
Here, na?
Using keyboard.
Okay.
using keyboard you can write there.
Okay, sir. vsudar. नहीं आ रहा है ना? हाँ, yes, vsudar @
Anurag ji, this video is not coming. That screen is not coming, not video, screen.
Screen it is not coming.
Screen तो बंद किया है. Screen is.
So then they
Sir, Monday, Wednesday I will write it on a this power.
Wednesday you give it.
next class
Wednesday I will write it on a.
next class you can give your email ID.
Yes, sir. Yes.
So let them go through these slides. Slides will be available.
Okay.
Okay,
Yes.
let them go through it, and next class you give your email ID so that they can ask a question directly.
Okay.
Okay.
Now we can discuss. Okay, Palta, thank you.
Thank
Thank you for
Anurag.
joining.
Thank you, Sudarshan. Thank you, Anurag.
Thank
Thanks
you.
a lot.
Thank you.
Okay. Manage this week. Next Monday I will be joining physically.
Okay, enjoy.
Enjoy. You also enjoy. Okay, bye.
Miss you.
I also miss you.
Okay.
Right. Okay, bye.